So welcome everybody. Good morning. This is Friday. This is class 30, I believe. That's some sort of milestone. It's a rather warm day in Toronto this morning. I had a nice bike ride along Bloor Street. I can see 199 of you here, so that's good. It's good to see you. Why don't we just get it going, I think. Share my screen. All right, so hopefully you can all see that. Let me put I'm showing there a Foucault pendulum, which is a really pretty cool demo, in which there's a big pendulum. We're going to be talking about pendula a bit today, and this pendulum is it's designed. Oh, it's not. There should be animation there. There's a little animation. It's designed to show every section numbers dwindle. Turn off that chat. That's good though. See you guys chatting. It's designed to swing back and forth. And when it's swinging, it's conserving momentum in that plane of momentum. And so what actually happens is as the Earth kind of rotates underneath the Foucault pendulum, you will see, if you're standing there on the Earth, you'll see what appears to be the Foucault pendulum plane rotating around once every 24 hours in the opposite direction from west to east. So it's a kind of a cool thing. It takes 24 hours for it to knock over all these little pegs. So we're continuing along to chapter 10. I guess we have to start with this, don't we? What's the polling? Yeah, I don't know. I'm just trying to, there's a limited number of Zoom video filters that I'm able to find in my Zoom. I'm not going to make the expression, obviously, that you see here. I'm just going to turn on the filter, but I thought it would be fun to, oh, I can make the, depending on who wins. I didn't put reindeer. Okay, everybody. Good. This is kind of silly. Just give me another 5 seconds. Okay. You got your vote in. Let's see what winner is. Mouse. Okay. I don't think we've done that before, so that's a good one. Let me find that filter. Under video. Filter. Mousey. Oh, that's long. Yeah. Where's mouse? There it is. Ada the mouse. I don't know what that means exactly. Who Ada is? Okay. And then another thing to note, I want to announce, I guess, is that the official course evaluations for H1F courses have begun. So an essential component of our commitment to teaching excellence is regular evaluation of courses by students. So I think it was actually this morning at 3 a.m. you were sent an email by courseevaluations@utoronto.ca inviting you to evaluate my course on Quarkus. It only takes about 10 minutes to answer the questions. There's a lot of them. You can answer, put your typed answers in for some of them, and some of them are multiple choice. Your answers and your thoughts are anonymous, but they're very important to me and also to Professor Seelfin, who will be reading them as well. She's going to be your professor for Physics 132 in January. So I promise you that when the results become available, we don't get to read them until the marks are submitted sometime about mid-January, but we will read them and scrutinize the responses to see if it can help us improve the course or our teaching in the future. They're important. And another thing that I will tell you, I've been at U of T for about 15 years now, and I've been the undergraduate chair, and I've served on a lot of hiring committees, promotion committees. University of Toronto takes course evaluations like this very, very seriously. It makes or breaks guys like me, and you can get, if someone consistently gets bad course evaluations, they will get fired and not stay at this university. If someone gets consistently good course evaluations, they'll get promoted and hopefully stay here rather than go to another university. So there's sort of a long-term benefit to evaluating your courses in that I think it helps teaching excellence flourish at U of T. Okay, so I want to talk about a comparison that is done in Akina of uniform circular motion compared to simple harmonic motion. So uniform circular motion, which we've done before, kind of looks like this. You've got a circle, or here is, we can put it on the origin of the circle, could be the origin of the XY axes. The radius might be, let's set actually the radius here equals A, just for fun. And then this thing will be moving around, so object moves with constant angular velocity, or angular velocity, omega, okay, in radians per second. How many radians this theta sweeps out per second? If this is theta here, and theta final equals theta initial plus omega times t. So if theta I equals 0, then and omega is 2 pi over t, then theta is equal to 2 pi over t times t. And so if you wanted to actually look at, for example, the x coordinate here of this object, this is theta, this is A, at some time, if this is x, then x is going to be equal to, I guess, if you look at cosine of theta is x over A, and x is equal to A times the cosine of 2 pi over t times t. So that's just uniform circular motion. Now, if you have a mass on a spring, here's a wall, and here's a mass m, and you define x as being measured away from some sort of equilibrium. A sub x we talked about last time is negative, well, it's going to be 4 pi squared over t times x. The trial solution here is that x is equal to A times the cosine of 2 pi over t times t, where A is constant. So I'm just saying here that mathematically, simple harmonic motion is identical to one component of uniform circular motion. And I'll just say that here, I will say that 2 pi over t is equal to the square root of k over m. I'm supposed to say here. A couple of people in the chat asked about the course evaluations. Is there a deadline? Yes, I think it's December 7th. Is it anonymous? Yes. Course evaluations are anonymous. Okay, good. Oh, December 10th. Thank you. Lauren just corrected me. Which is good. Okay. Next thing is sort of this mysterious thing. You get asked about VMAX, the maximum speed of simple harmonic motion, a lot. You also get asked about AMAX, the maximum acceleration. So, but she doesn't really give it in the text, and so I'll just point it out here. She does give this x. X is A times cosine of something, okay? And so what I would say is, I would say note that cosine of theta varies between +1 and -1. So what that means is whatever this thing is, it's going to get up to +1 and down to -1. So the x max, you know what it is? Biggest it can get is A. Okay. And then she does give these equations for velocity and acceleration as functions of time. But you're not often asked in problems for what are these things as a function of time. You're asked for what's the maximum speed, what's the maximum acceleration. And so again, you can use the same thing, same for sine theta. It varies between +1 and -1. So what this means is that, forget about all this stuff, VMAX is equal to, and forget about the negative sign because you can go to -1, it's just going to be 2 pi over t times a. That's the maximum speed. And that's a useful equation. These are useful equations to have. And then this one, again, forget about all the cosine stuff and the negative. It's going to be A max is equal to 2 pi over t squared times A. Okay. Robert has pointed out that these are just actually time derivatives. First time derivative, so v is the time derivative of x and a is the time derivative of v. But it's an algebra-based course, so I'm not doing that. Okay. So A here is the amplitude of the vibration, T is the period of the vibration. And what I will do, let's actually do a poll. Okay, the body mass measurement device chair, which has a mass of 32 kilograms, has a vibrational period of 1.2 seconds when it's empty. But then this astronaut right here, Tamara Jernigan, sits in it. And then it oscillates again with the same spring constant. What will be the vibrational period? Will it, when she's sitting in it, should be more than 1.2 seconds, less than 1.2 seconds, or exactly 1.2 seconds? To think about that. And then let's actually solve it. I think what I'll do is okay. Once and twice and polling. Share results. So 58% of you maybe had the intuitive feeling that it's just someone sitting in it, there's more mass there, it's going to slow down the oscillations. So that's absolutely correct. And if you want to look at the actual equation from the book, it is T is equal to 2 pi, oops, sorry, 2 pi times the square root of m divided by k. So as it gets bigger, the period gets longer. It takes longer for it to go back and forth. And this is actually how astronauts measure their own mass when they're up in the space station. They have to do a lot of exercise and watch what they eat, try to not lose their muscle mass and things, and to stay healthy. They can't stand on a scale because they're in a weightless environment. So they go in a thing that shakes them back and forth and measure the period. So let's say that you've got a body mass measurement device chair, where the mass of the chair is equal to 32 kilograms, has a vibrational period of the chair only is 1.2 seconds when it's empty. But when the astronaut sits in the chair, mass of the astronaut is equal to question mark, which you're trying to find, the period changes to chair plus astronaut is equal to 2.1 seconds. So basic idea here is that if you do the system is equal to the chair plus spring, and what it looks like, you've got there's some sort of wall, which I guess is attached to the rest of the space station wall, and you've got this mass of the chair, and it goes back and forth with TC. The second system will be chair plus the astronaut plus the spring. In that case, again, you've got the wall, here's the spring, And here's the mass of the astronaut plus the mass of the chair. And it goes back and forth with some TCA. Okay. And so what I think I'm going to do is I'm going to use equation 10.7 from page 294 of your book, which is that T is equal to 2 pi times the square root of m over k. And I'm going to use the system 1. I'm going to solve for k. Because you know mass and you know T. And then I'm going to use system 2. I'm going to solve for mass. Mass of the astronaut, I guess, right? Which is the mass of that, what we're trying to get. So from system 1, I will say TC is equal to 2 pi times the square root of the mass of the chair divided by k. K is going to be the same spring constant in both. I can divide both sides by 2 pi, square everything. TC squared over 4 pi squared is equal to MC over k. So what that means is that k is equal to 4 pi squared times the mass of the chair divided by TC squared. And then if we look at system 2, you've got TCA, both of them together is 2 pi times the square root of MC plus MA divided by K, same spring constant though. Again, divide by both sides by 2 pi and square the thing. TCA over 4 pi squared is equal to MC plus MA. This is to get rid of the square root sign, right? And then I'm going to times over by K, both sides by K. I'm going to have to say, let's rearrange it a little bit. MC plus MA is equal to K over 4 pi squared times T CA squared. And actually, I can from here just find what K over 4 pi squared is. It's equal to MC over TC squared, right? So I can kind of plug that, and I can say that what are we trying to find? MA is equal to K over 4 pi squared times TCA squared minus the mass of the chair, I think. So I can take this from system 1 and just plug it into right there. And I'll get the mass of the astronaut is equal to MC times TCA squared over TC squared minus MC. So there's an MC, and then you times it by TCA over TC all squared minus 1. So the mass of the astronaut is equal to 32 kilograms times 2.1 over 1.2 squared minus 1, and I got 66 kilograms. And this turns out to be about 145 pounds, reasonable for an astronaut. Yeah, there's a lot of different ways of doing this. You can use ratios instead of solving for K. I like to solve them for K. Ava, how are you doing up there? Do you want to unmute?
Hi, yeah, I was wondering, for the second line on the side with equation 2.
Yeah.
How did you get 4 pi squared in the denominator?
So I divided both sides by 2 pi, and then I squared both sides to get rid of the big square root sign.
Oh, okay, thank you.
Yeah, you're welcome. Sort of did it a little fast, but 2 pi all squared is 4 times pi squared. So, okay. I wanted to, well, let's move on to energy. So section 10.4, and I think we're going to do a few team up questions about energy. So this is about energy of vibrational systems. So what happens as this thing oscillates back and forth is that, well, I think we started it actually at t equals 0, and we said that the displacement is plus a, and we release it from rest. So when you release it from rest, the kinetic energy is 0. Okay? So that's kind of the start. But when you do that, the spring has been stretched by some amount, x equals a. And so there's potential energy stored in the spring, which is 1/2 kx squared. And we talked about that earlier. It's, I guess, the work done on this spring as you pull it out that distance. So this is U sub s, potential energy of the spring. And then when it comes back to that same thing, and one period later, it's again going to be 1/2 k squared. But if you look at, as it speeds up, a quarter of the, this is like, I don't know why they're all in a weird order here, but at a quarter of the period, the thing has moved backwards until it's going as fast as it's going to go right at the 0 point. The spring at that moment has 0 x, right? So it's not compressed and it's not stretched. So there's no potential energy, but it's moving as fast as it will go. So it's moving at 1/2 m VMAX squared. And then it'll go all the way 1/2 period. It'll be at negative a, and it will have stopped. But again, since there's a squared here, negative x is negative a, but negative a squared is a squared. So you're at positive 1/2 k a squared. And if you add these up, you always get the same total at all these different points. Excuse me. Sorry for that. Luckily, you're not going to catch my COVID because you're not here. Not that I have that, but okay. And what turns out is that even in between these maximas, the green line here is the potential energy, which is that U is equal to 1/2 kx squared. And the green line is the kinetic energy, K is equal to, I should make it angry. Kinetic energy is equal to 1/2 mv squared. So x and v very smoothly, right? Because they're both cosine functions as this goes up and down. But when you add cos squared plus sine squared, as it turns out, you always get this constant value. And so I'm not going to go through the whole math of it, but it's always this constant, which is either this or that. So I'll put it here. So E equals the kinetic energy plus the potential energy, spring potential energy is constant. Okay. And it's either, you can use either equation, whichever is more convenient. You say the total energy is equal to 1/2 m Vmax squared, or the energy is equal to 1/2 k times a squared. You can use whichever one of these equations is most convenient for you, depending on what you've been given. I just looked at my chat window and there's about 15 bless yous. I appreciate that. I feel very blessed. Andy? Did you want to unmute?
Sorry, that was a misclick on my part.
Yeah. Oh, I see. Okay. Okay. Good. So this is sort of what it looks like. There's this constant energy, and then what actually happens is that there's these turning points at the ends, and there's a parabola here, which is that this thing goes back and forth. Okay, on this U spring is equal to 1/2 k x squared is a parabola. Okay. So it just sloshes back and forth. You can also rearrange this to find another equation for Vmax. Vmax is the square root of k over m times a. And this makes sense conceptually because if the mass of the cart is large, then it moves more slowly, I guess, given the same spring constant. But if the spring is more stiff, then it moves more rapidly. So what we're doing here is that we're neglecting friction. So once again, you've got a mass that's sitting on a horizontal surface, is going back and forth. and it's a frictionless surface, so there's no dissipation of energy. That's why the total energy is constant. In reality, what you've got, if you've got friction, is that total energy will decrease steadily as the energy dissipates. And we'll talk about that more on Monday. I think you have everything that you need now for this team up quiz. So I think it's going to be team up time. Oh, yes, we're still doing this. Remember this business? This is going to be after the thing. So this is something to discuss if you guys have extra time in the team up. This Queen's Gambit versus Tiger King, or the Good Place versus Parks and Recreation. Then, you know, winners of these 2 votes, there's going to be 1 vote next Friday, which is our last Friday. Okay, so today we'll be doing 3 multiple choice questions, all from chapter 10, as teams of 2 to 4 students in your practical pod. Your pod team shares the mark. Right now, the way to do this, you open up your Microsoft Teams. Someone should place a call on the side there. I'm going to mute myself soon. And then you all have to go to this team up quiz. So in your call, decide it's going to be the driver. Non-drivers, please wait as the driver starts the team up quiz and creates a new group, and then comes back to you. The drivers should go back into your team up window, your Microsoft Teams window, and type the session ID, and then all the other members join in. Go to Quarkus, log into team up, and join in the same session. Once everyone in your room arrives in the team up quiz, try to achieve consensus. Talk about these. I think the first 2 are more conceptual ratios, and the third one is going to really involve a little bit of work, and you should try to think about it. It's actually, there is a very simple way to do the third problem if you know which equation to use. So to have a talk about that. If your podmates are not available and they're not answering the Microsoft Teams call, you could go to the Physics 131 Help Center, and I'll put you in a group with 2 other students, and you can meet somebody new. So, and I'm gonna come back here at 11:47. So, and I'm gonna mute myself. If your podmates don't join the call, then just try to hop on another Zoom, I guess, with the Physics 131 Help Center, and I'll help you out there. So. So before we talk about the team up questions, I'm going to do this silly television thing. It's going to be 15 seconds things. So I'll just do Queen's Gambit versus Tiger King. Relaunch polling. Five, 4, 3, 2, 1, 0. That was, just to give you the results here, 71% versus 26%. So Tiger King is out. And then Good Place versus Parks and Recreation. A lot of people were lamenting the fact that Schitt's Creek was gone last week. 3, 2, 1, and polling. So there you go. 65% versus 31%. So out goes Parks and Recreation. Okay, so it'll be Good Place versus Queen's Gambit next time. Okay. So, but seriously, that's got nothing to do with physics. I mean, the whole idea there, why am I doing any of this? What I'm hoping is that you guys talk about more than just physics, and that you actually meet some real friends in this class somehow, maybe in your practical pods, or, you know, in some way, study groups or something. I think a big important part of university is the people you meet. And I remember very clearly meeting people, and I have still friends that I met in first year at U of T. So. By what factor must we increase the amplitude of vibration of an object at the end of a spring in order to double its maximum speed? So the VMAX here There's lots of equations for this, but the one I'm thinking of is 2 pi over t times a. Okay, and t is a fixed number, right? So if t is if t is a fixed number, then you double a, you're double v, right? So it's just v. And then the other question is, by what factor must we increase the amplitude of vibrational object in order to double the total energy? So this one is the E is equal to 1/2 k times a squared. So it's, you're trying to get the square root of 2. Yes, I think I'm recording. Thank you, Alex, for the meeting's recording. Okay. And then this one was the hard one. So if we have a mass on a spring, again like this, here's a wall, here's the mass. M is the thing, M is unknown, okay? But K is 200 newtons per meter. And it says that X is this thing, but I know that X is equal to the A times the cosine of 2 pi over capital T times lowercase t. So what this means, if I just compare this equation to this equation and like compare, then you can see right off there that A is equal to 0.35 meters and that 2 pi over T is equal to 15, whatever the units are. Now I happen to know, I do a lot of physics, the units here are radians per second, but anyways, doesn't matter, it's something per second. It's 15 SI units. And then what else? So actually what we're actually to find is the E. So E equals 1/2 m times VMAX squared, or E is equal to 1/2 k times a squared. So you can pick one of those depending on which one is easier. So to me, you're given k, you're not given m, and you're given a is right there. So let's use this. Easiest, you can use either one, but it's easiest to use this. And then you got 1/2 times 200 times 0.35 squared is equal to 12.25. So I got D. Okay. And Sunny's been asking, the amplitude is equal to the maximum displacement away from equilibrium. So maximum value of x. And the amplitude is a constant. Okay. I want to talk a little bit about time here. We've got to be a little careful with time. Yeah, so let's just look at this. What is the net torque on this pendulum? So what we have is a situation where you've got a mass that's on a string. That's called a pendulum. And what we can do is we can say that this is the axis of rotation. And then you've got a mass going around in a circle. And so we can sort of give a force diagram plus here of here's an object, here's the T, the string on the mass, okay, and here's the force of gravity of the Earth on the mass, which is mg. So the torque from the tension is 0. And the reason for that is that if I take a force line through the tension, it's going to go straight through. Oh, I didn't do it that way. It should go straight through the rotation axis, right? Does that sort of make sense? Because the tension is up the string and the string is connected to the rotation axis. So whenever the force line passes through the axis of rotation, then the lever arm is 0, and so the torque from tension is 0. So all the torque actually comes from gravity. So some of the torques is from gravity. And you can actually work out if this is mg, the lever arm right here X is equal to, it's going to be L times sine of theta, roughly. So the torque here is equal to mg times L times sine theta. So, and wait, sorry, that's clockwise. Sorry, clockwise is negative. Since it is clockwise. Okay. So, suppose we restrict the pendulum's oscillations to small angles. Then you can use this small angle approximation, which is sine theta is approximately equal to theta when theta is measured in radians. So the net torque, which is negative mg L sine theta, is approximately equal to negative, this is the approximately equal to mg L times theta. So the simple harmonic motion equation is that alpha is equal to negative some big constant times theta. So the solution here is theta equals a times the cosine of 2 pi t over t, where a is a constant, and the period of oscillations is 2 pi times the square root of I, the rotational inertia, divided by mgl. But this is just a mass away, a distance L away from the center has rotational inertia of ml squared. So I plugged this all in, and I've got that the period is 2 pi times L over G, square root of L over G. So I think what I want to do is actually do a quick couple of demonstrations, and then we'll end this up. So I'm going to stop the share. I want to show you a couple of things. So these are some pendula over here. Let's see if we can see them all. So what I've got is a few different pendula. So these pendula are the same length. So if I pull them to the side, pull them to the side and release them, they swing together. Same length, same period, because they have the same length. If I take these two pendula, forget about this one for a second. This one has a longer length. This one has a shorter length. I pull it to the side. Remember, it's square root of L over G. So, oh, sorry. Point is that they're not. So the one with the longer period, the longer string, has a longer period. Which is this one. And this one is a shorter string, so it's oscillating faster. We can also look at these masses over here. And again, I have to kind of shout. But what we've got is two springs that are the same. So if I hang the same mass on them and pull them down, these are both 500-gram masses, they'll oscillate together, the same frequency. If I increase the mass, this is now a 1 kilogram mass. First of all, it hangs lower. If I release them together, this one has a longer period. More mass, longer period. And then the other thing we can do is use a different kind of spring. So this is a spring that has a lower spring constant. So the value of K is lower, it's less stiff of a spring. So when I release them, same mass in both cases, the smaller value of K gives a larger period. That's on the denominator then. So then, square root M over K. Okay, everybody. Just to see where we're at here. Share this screen here. Okay, I would like you to finish reading chapter 10. On Monday, I'm going to finish up chapter 10. I'm going to talk about damped and driven vibrational motion. Maybe work on a couple simple harmonic motion problems like you might see on the midterm. Midterm number 5 is on Tuesday at 8:10 p.m. It's based on chapters 9 and 10. It'll be 10 multiple choice questions, one at a time. There'll also be a question from the practicals on some of the practicals you did in practicals 4, some of the stuff you did. So have a great weekend, everybody. It's been a good week, and I'll see you on Monday. Hope everyone has a good. And then what I'm going to do is I'm going to turn off the recording.